Now we're going to talk about strength of the association, and the tool we use for that is correlation. And what is correlation? So first of all, I've got my original points here, A, B, C, D, and E. It doesn't matter what order they're in. And I can move them around if I want, okay? And what you're seeing here, there's some points over here. How did we get these points? Well, first of all, I have a mean point marked here. I'm going to move this a little further away from the mean. You can see it right there. And that's taken, we figured that one out by determining the averages of the x-coordinate and the averages of the y-coordinate. So that's the mean. So that's the average of all these in both the x and y direction. We also can calculate the standard deviation for the points, and you can see those calculations right here. So you would expect 68% of the points to be within 3 of this mean point, all right, depending how far out. If it was a normal distribution, but it's not because I'm moving points around. Same thing for standard deviation in the y. So here's the average between the points, and this is how far out the spread. This is a measure of spread vertically. Now, if I put this C point, let me try and get it really close to the mean point. Notice where it lands on this other graph for C prime. Basically, these prime points, we're measuring how far they are from the mean and the number of standard deviations. So most of your points should be less than 2 standard deviations away, unless you do something like this and put somebody really far away. So, and even then, it's still, look how hard it is for me to get this one point. I group this all up. It's very hard for me to get this one point more than 2 standard deviations away, right? Even when I've got all these almost on top of each other. So most of the time, they're going to be within 2 standard deviations. All right. So anyways, let's go ahead and put these points back. And we'll say, hey, I want to see if there's some sort of linear relationship. And this looks as good a combo as any. All right. And what could we determine, does a linear fit well with this? So basically, what we do is we plot these points out, and we're kind of looking at the slope of the line that would go through these points. So the closer this is to being a tight fit, the higher the value, the absolute value of the slope. Now, why is this slope negative? Well, if you look at it, the x value here is below the mean. It's below the average, so my z-score would be negative here. But my y value is above the average, so it'd be positive, okay? So there's sort of, when y is positive, x tends to be negative. When x is positive, y tends to be negative. That's why we have a negative correlation here, all right? So we can move the points around. If I really have no correlation, let's just say it's just a bunch of points sitting around like this, you can see that my correlation value goes down to 0. So we had a negative correlation when we started. And now let's say I want to make it look a lot like a line. So I'm going to move these points around. Okay. I know I'm going through my thing there. And, oops, I didn't mean to move my mean point. And let's say the way I'm going to do it is I'm going to kind of just bump them up. So you can see here, this looks really linear, right? And what's my correlation running at? It's at 1. That is the strongest the correlation can be, is 1. And if you look at it, there's a very strong, what they're looking at is this here. So there's a very strong correlation. When x is above average, y is above average. And it's about the same number of z-scores, all right? When x is below average, y is below average by the same number of z-scores. So when the z-scores are the same, oh, that's 45 degrees, which, by the way, is a slope of 1 for this line. Notice that the slope of this blue line is not necessarily the same as the slope of this green line here. And we'll talk about that actually in the next chapter. So you can actually calculate these correlation points by hand. Don't do it. Don't do it. Your calculator will do it. But here's the formula for correlation. You take your z-score for a point times in the x direction for the z-score in the y direction for the same point, and you multiply them. which kind of makes sense. So when we had, let me go positive again. So my D is above average in X and Y, so I'm going to get a positive product. And it's kind of high, so I'm going to get a big product, right? Here, my A is below average, there's my average, in both X and Y. So I'm going to get negative times negative is positive. So these are going to give me primarily positive scores. If I had a negative correlation, what happens is, I'm making these points linear, all right? Here, when D is below average, here D is above average in X and below average in Y. So X would be positive, Y would be negative, the Z-scores anyways, and I would get a negative product, okay? By the way, if I have a point right at the mean, it has no effect on the products or the correlation. So, because the Z-scores are 0, which is also interesting. Okay, so now that we've talked about correlation, the next thing you need to know are some properties of correlation. As we already mentioned, the correlation coefficient is always between -1 and +1. It can go to -1. That means it's a perfectly linear negative relationship. It can be +1, which means it's a perfectly linear positive relationship. So again, when R is less than 0, negative correlation and negative direction. We talked about direction on the last video. When R is positive, positive correlation and positive direction. The cool thing is you'll get the same R value even if you flip the explanatory, which is the X, and the response, which is the Y variables. And since we measure correlation in Z-scores, remember, it's not going to be affected by scale or center. One thing I'm going to show you in just a sec is that the correlation is sensitive to outliers. And I'll show you how that works. And remember also that it only measures linear association. We don't do this for exponential growth, quadratic, whatever, logarithmic, none of that. So I'm going to show the effect of outliers here. I put all these points kind of close together. All right. And I'm going to move this one point. Oops, sorry. Helps if you move only original points. So let's say I take point E here and move it way out. All right. You can see my correlation got really close to 1. And what's going on is these products are kind of small. This product is huge. It's like 2 times 2, it's 4. Whereas these products are not having a big influence on it. So even though you could argue, hey, this doesn't look very, if I didn't have point E, right, it doesn't look very linear at all. So if point E was just right where the mean is, there might be a little bit of a correlation, and you can see that my correlation drops down. But when I pick up point E and move it far away from my other points, my correlation gets stronger and stronger. So if you have a really high correlation, check for outliers, because that might be influencing the correlation. Not only that, remember, we don't like to look at points that are more than 2 standard deviations away from the group. So I could even move these points, all of them over here. Oops, sorry, not the mean. I'm going to move all these points except for E. So I'm going to try and make them even further away. All right. Notice I've got a correlation of 1 when that's kind of scattershot down here. So the further away it is, and here I'm still on the edge of 2. I wonder if I can delete the point. Nope. So anyways, when I delete it, then obviously the correlation disappears. So now for linear, so it's only for linear association. So again, I've got these points scrambled around. Let me do this. I'll move some of them around. Not my mean point. And keep grabbing my mean point. Let's say it was a little bit quadratic, or better, yeah, let's just say it's a little bit quadratic. What's my correlation? It's -0.01, which is kind of close to 0. So it implies that there's no correlation between X and Y here. But you can see this probably could be parabolic. If the association is not linear, correlation is useless, all right? So it's only for linear relationships. Now, how do we do this on our calculator? First of all, the calculators don't automatically do correlation when you pull them out of the package or after changing batteries. We need to turn something on called diagnostic. So to do that, you're going to press second catalog, which is the 0 key. And then you're going to scroll down for quite a while until you get to diagnostic on and press enter. All right. And when we get there and press enter, the calculator will display done. Almost there. There we are. Press enter, hit enter again, and we're done. All right. Now, to take our data, choose calc from the menu and go down to, oops, says 8 here. It should be 4. Change that to 4. Line reg a plus bx. It must have been a different version of the book, so I'll change that on my printout, but that's supposed to be 4. Pointer options, pen, that's 4. All right, press enter. Specify the x and y with second list names. Make sure you put a comma in there. See how I'm going second list names to do that? And press enter. Okay, so I will play that again. Pointer. So if I go and play that again, let me show you where we did that. So you go line reg, right? And do second list. Scroll down to your names for your variables. This is the same example we did on the last video with calories and fat. Put your comma in, which is down there. And then go ahead and put in the other variable for y, which is your response variable. And then hit enter. And you can see the correlation here is 0.96. Well, 0.96 actually indicates a strong linear relationship in the positive direction. Remember, the highest value we were able to get for correlation was 1. And 0.96 is pretty close to 1. Now, there is an outlier here. So I could say, I'm a little suspicious I've got an outlier. So how do I remove the outlier? Go ahead and get your data. And you see that delete button right there? If you hit that, it will delete the points. Now make sure you always have the same number of values in both columns, or the calculations won't work. So now we're going to go ahead and do the correlation again for this. Second list, and then come down to calories. And second list, after the comma, of course. Do the fat. And let's see what happens to my correlation. I got 0.83, 0.86. So even if we take the outlier out at 410 calories and 19 grams of fat, the correlation of 0.837 is still pretty strong. All right. By the way, again, remember correlation will be the same whether I did fat versus calories or calories versus fat. So I've been using the word strong. When can we say something is strong? Well, it depends. Outliers can inflate R, so be careful there. But in a pinch, you can use the following general guideline. If it's between -0.8 and -1, that's a very strong negative correlation. Between 0.5 and -0.8, that's a moderate negative correlation. Weak is anything from -0.5 to +0.5, which is pretty much half your range. Moderate is positive would be 0.5 to 0.8, and strong would be 0.8 to 1. All right, that's just a general guideline. You should always look at your data to make sure there's not some other reason that you're seeing the correlation. Remember, zero correlation doesn't mean that there's no association. So don't mix up association and correlation. So let's take a look at 2 other examples really quickly. A researcher, this is number 24 in your book, investigating the association between 2 variables, collected some data, and was surprised when he calculated the correlation. He expected to find a fairly strong association, yet the correlation was near 0. Discouraged, he didn't bother making a scatter plot. Explain to him how the scatter plot could still reveal the strong association he anticipated. Well, as we just said, the correlation might be nonlinear, resulting in a correlation close to 0, even if there is a strong association. And also, maybe there's an outlier that is affecting things. All right. So in this example, we've got average finish times versus age. And you can see there does seem to be a correlation with age and finish time, but we have this one outlier, which is giving us a very low correlation. In our next example, it's problem 32 in your book. A polling organization is checking its database to see if the two data sources they used, not sued, sampled the same zip codes. The variable data source equals 1 if the data source is Metromedia, 2 if DataQuest, and 3 if Rolling Poll. They find a correlation between 5-digit zip code and data source is negative 0.0229. It concludes that the correlation is low enough to state there's no dependency between zip code and source of data. And we ask you to comment. Well, first of all, the data source is categorical. These numbers of 1, 2, and 3 are just sort of a sign. Could be, if you could do a correlation, even though it's meaningless here, it might change if you switch 2 and 3 or 1 and 3. So actually probably 1 and 2. So there's no way to use correlation for this. This is categorical data. Some extra problems for you to practice. Try problems 11, 15, and 33. And the answers to those are in the back of the